Welcome back. Last time, we did implicit differentiation and related rates, letting curves that refuse to be functions tell us their slopes, and watching the chain rule connect rates in time. Today, we take the simplest possible observation in all of calculus and milk it for everything it's worth. The observation is this: a smooth curve, viewed up close, looks like a straight line. Not is a line. Looks like. But for the purposes of computation, the difference between a curve and its tangent line, over a small interval, is small enough that we can throw it away. That throwing away is called linear approximation. The line has a name, the linearization, L of x, and a formula, f of a plus f prime of a times x minus a. We'll derive it, use it to approximate the square root of 9.04 in one line, estimate 1.02 to the 10th without expanding a polynomial, and propagate measurement error through the volume of a sphere. We'll also resurrect a notation you've seen 100 times, dy equals f prime of x times dx, and finally take it literally. The history runs from Leibniz to Newton to Cauchy to the modern view. The payoff is that every linear circuit model, every small signal approximation, every linearize around equilibrium in engineering is exactly this episode. Let's go. The big idea, stated as bluntly as possible. Take any smooth curve, pick a point on it, zoom in. As you zoom, the curve flattens, the wiggles vanish, and what you see in the viewport stops looking like a curve and starts looking like a line. Which line? The tangent line at that point, the one whose slope is f prime of a. This is not a coincidence, it's the geometric meaning of the derivative. When we say the derivative exists at x equals a, what we mean, precisely, mathematically, is that the curve admits a best linear approximation there. So the strategy is obvious. If we want to estimate f at some nearby x, and the curve f is hard to evaluate by hand, replace the curve with the tangent line and evaluate the line instead. Lines are easy. Y equals mx plus b. One slope, one intercept, mental arithmetic. The curve might involve square roots or exponentials or trig. The line doesn't. We trade a hard curve for an easy line, accept a small error in exchange, and walk away with an excellent estimate. That trade is the whole episode. Here's the formula. We want the equation of the tangent line to the graph of f at the point with x-coordinate a. The line passes through the point a, f of a. The slope of the line is f prime of a, by definition of the derivative. Use point-slope form. The equation of the line is L of x equals f of a plus f prime of a times the quantity x minus a. That's it. That's the linearization. The capital L is convention. For linearization or linear approximation, take your pick. And for x close to a, we claim f of x is approximately equal to L of x. The approximation gets better as x gets closer to a and gets worse as x drifts away. Look at the formula structure. 2 ingredients. The value f of a tells you where the line starts. The slope f prime of a tells you how it tilts. Together, they pin down the line completely. To use the formula, you need to evaluate f and f prime at one convenient point a, usually a round number where the arithmetic is easy, and then you can estimate f at any nearby messy point. Picture. The blue curve is y equals f of x. The red line is the tangent at the point a, f of a. Step to a nearby x value, a plus dx. The curve rises by some amount we'll call delta y, capital delta y, the actual change in f. The line, over the same horizontal step, rises by dy, the predicted change according to the tangent. Visually, you can see they're close but not identical. The tangent line undershoots the curve slightly here, because this curve happens to be concave up. The gap between the blue arrow and the red arrow is the approximation error. As dx shrinks towards 0, that gap shrinks faster than dx. It goes to 0 faster, which is the precise statement of differentiability. For small dx, the gap is negligible, and we can pretend the curve and the line are the same. That pretense is what we're going to cash in for the rest of the episode. One more picture to lock the intuition. 2 panels. On the left, a curve and its tangent line at the wide scale we're used to seeing. The line and the curve part ways visibly as you move away from the point of tangency. On the right, the same curve and the same tangent line, with the viewport zoomed in by a factor of 20 around the point of contact. At that scale, the curve and the tangent are visually indistinguishable. You can't tell which line is the function and which is the tangent. That visual fact, the 2 graphs becoming one as you zoom, is the geometric content of differentiability. And it's the reason linear approximation works. In a small enough neighborhood, the line is the curve. You're not making an error so much as choosing a different but equivalent picture, where the arithmetic is easy. Why does this work? Why is the tangent line a good approximation at all? The answer is that this is exactly what differentiability means. Here is the definition, written in a form most textbooks don't bother with, but you should see at least once. A function f is differentiable at a if there exists a number, call it f prime of a, such that f of x equals f of a plus f prime of a times the quantity x minus a plus an error term, epsilon of x times x minus a, where the function epsilon of x goes to 0 as x approaches a. Read that slowly. The function f equals our linearization, L, the first two terms, plus an error that vanishes faster than x minus a. The error doesn't just go to 0, it goes to 0 divided by x minus a, faster than linear. That's what makes the tangent the best linear approximation. Any other line through the point would have an error that stays comparable to x minus a, not smaller. Only the tangent has error that beats linear decay. So the formal definition of differentiability is, the curve admits a best linear approximation at the point. That's it. Everything else, the limit of the difference quotient, the slope of the tangent, is just unpacking that one statement. First example. Estimate the square root of 9.04 by hand, no calculator. Set f of x equals the square root of x. We need a nearby point a where the square root is easy, and obviously that's a equals 9 because the square root of 9 is 3. Compute the two ingredients. F of 9 equals 3. F prime of x equals 1 over 2 root x, which at x equals 9 is 1 over 6. So the linearization at a equals 9 is L of x equals 3 plus 1/6 times the quantity x minus 9. Plug in x equals 9.04. The quantity x minus 9 is 0.04. 1/6 of that is 0.00666, repeating. Add 3, get approximately 3.00667. Now check against the truth. Pull out a calculator. The actual square root of 9.04 is 3.006659, and so on. We got 5 decimal places of agreement from a one-line hand calculation. The tangent line, evaluated at a point only 0.04 away from the base, is essentially as good as a calculator. This is the power of linear approximation in its simplest form. Second example with a twist. Estimate 1.02 raised to the 10th power. Set f of x equals x to the 10th. Choose a equals 1, where f of 1 is just 1 and the derivative is easy. F prime of x equals 10x to the 9th, so f prime of 1 is 10. The linearization is L of x equals 1, plus 10 times the quantity x minus 1. Plug in x equals 1.02. The quantity x minus 1 is 0.02. 10 times that is 0.2. Add 1. The linear estimate is 1.2. Now check. The actual value of 1.02 to the 10th is 1.2189, and so on. We got 1.2 close, but the error is about 0.019, which is roughly 1.6%, worse than the square root example. What happened? Two things. First, x minus a was a bit larger relative to a 2% of 1 versus less than 0.5% of 9. Second, the function x to the 10th curves much more aggressively than the square root near these respective base points. Look at the second derivative. For x to the 10th, f double prime is 90x to the 8th, which at x equals 1 is 90. Half of 90 times the square of 0.02 is 45 times 0.0004 equals 0.018. That's almost exactly the error we observed. The second order correction we missed accounts for the shortfall. Linear approximation is the first order story. Higher order corrections, Taylor series, are how you drive the error to 0. That's a future episode. Now meet a notation you've been staring at for 9 episodes and we'd never quite explained. The tangent rise, dy, and the horizontal step, dx, are related by dy equals f prime of x times dx. Read this as, a tiny change dx in x produces an approximately tiny change dy in y, and the proportionality constant, the conversion factor, is the derivative. There are 2 ways to interpret this equation, and both are useful. First interpretation, the symbolic one. We've been writing dy over dx as shorthand for the derivative, and treating it as a single symbol. In that view, dy and dx separately don't really mean anything. They're inseparable bookkeeping. This is how rigorous calculus courses sometimes present it. Second interpretation, the literal one. Treat dx and dy as actual quantities. Small quantities, maybe infinitesimal, that's Leibniz's original idea, or maybe just a linear approximation to the change. On this reading, dy equals f prime of x times dx is a regular algebraic equation, with 3 honest numbers in it that you can manipulate, multiply, integrate, and reason about. The literal interpretation is computationally lethal. Engineers, physicists, applied mathematicians use it all day. The symbolic interpretation is what you fall back on if you want to be rigorous and you don't have the modern machinery. We'll be literal for the rest of the episode. A historical aside, because the symbol dx has had quite a life. In the 1670s, Newton developed calculus under the name of fluxions. He called the infinitesimal increments moments of the flowing quantities. They were treated as indivisibly small, smaller than any positive real number, and Newton was uneasy about them but used them anyway. In 1684, Leibniz independently published calculus in essentially the notation we use today. His dx and dy were called differentials, also treated as infinitesimal quantities. Leibniz's calculus was wildly productive. Much of the calculation we still teach is Leibniz's, but it was also logically uncomfortable. Mathematicians of the 18th century used infinitesimals because they worked, while flinching at the fact that nobody could say what an infinitesimal really was. That stayed unresolved until the 1820s, when Cauchy reformulated calculus on limits using the epsilon delta machinery you may have suffered through in analysis class. Infinitesimals were expelled. The symbol dy over dx became one indivisible symbol with no separate meaning for dy and dx. That was the conservative orthodoxy for a century. Then, in the 20th century, dx got rehabilitated, twice. First, Élie Cartan developed the calculus of differential forms in the 1920s, and on his interpretation, dx is a linear map from tangent vectors to the real numbers. It's a legitimate algebraic object, and dy equals f prime of x times dx is an honest equation of differential one-forms. Second, Abraham Robinson in 1960 invented non-standard analysis, which constructed a rigorous number system that includes actual infinitesimals, vindicating Leibniz 3 centuries late. Modern mathematicians use whichever interpretation suits the problem. The point is, dy equals f prime of x times dx is respectable. Use it freely. Third example. The application that makes differentials indispensable, error propagation. You measure something with finite precision, a radius, a length, a voltage, and you compute a derived quantity from it. How does the measurement uncertainty propagate into the computed quantity? The differential gives the answer in one step. Concrete setup. You measure the radius of a sphere. Your instrument reads 10 centimeters, plus or minus a tenth of a centimeter, so r equals 10, and dr is plus minus 0.1. Question, what is the uncertainty in a sphere's volume? Volume of a sphere is 4/3 pi r cubed. Differentiate, the derivative of v with respect to r equals 4 pi r squared, so dv equals 4 pi r squared times dr. Plug in, r equals 10, so r squared is 100. 4 pi times 100 is 400 pi. Times dr, which is 0.1, gives 40 pi cubic centimeters. Numerically, 40 pi is about 125.7 cubic centimeters, so the volume uncertainty is plus or minus about 126 cubic centimeters. Now put that in context. The volume itself, 4/3 pi times 1000, is about 4,189 cubic centimeters, so we have 126 out of 4189, which is about 3%. Meanwhile, the relative uncertainty in the radius is 1/10 out of 10, which is 1%. 1% in the radius became 3% in the volume. The factor of 3 is no accident, it's the exponent of r in the volume formula. In general, if a quantity is r to the n, then relative error in the quantity is n times relative error in the input. We just rediscovered the logarithmic differentiation rule, hiding in plain sight. Why this episode matters more than it looks. Step into any engineering discipline, and at some point you'll run into a nonlinear problem that is too hard to solve directly. The universal trick, linearize. Pick an operating point, an equilibrium, a steady state, a DC bias, and replace the nonlinear function with its tangent line there. Suddenly, the problem is linear, you can solve it with matrices, and you get an approximate answer that's correct as long as the deviations from equilibrium stay small. Examples are everywhere. Electronics, a bipolar transistor has a strongly nonlinear voltage to current relationship, but at a fixed DC bias, small AC signal perturbations see a locally linear amplifier. That entire branch of circuit design, called small signal analysis, is one episode 10 operation per device. Classical mechanics, a pendulum satisfies a nonlinear equation involving sine of theta, but for small theta, sine theta is approximately theta. That's the linearization of sine at 0, and the pendulum becomes a simple harmonic oscillator. Control theory, almost no real system is linear, but linearizing around a desired set point lets you use linear control design, which we actually understand. Numerical methods, Newton's method for finding roots is literally follow the tangent line to its x-intercept and iterate. Linearization, applied repeatedly. Differential geometry, the tangent space at a point on a manifold, is the linearization of the manifold itself, formalized. The pattern repeats everywhere. Every time anyone in engineering says for small perturbations, or to first order, or in the small signal regime, they're invoking this episode. A word on when linear approximation breaks down, so you know what's safe. It works whenever f is differentiable at a, meaning the curve has a well-defined tangent line there, and the step x minus a is small relative to the curvature of the function. Small relative to curvature is the right way to say it. Small in absolute terms can be misleading. A step of 0.02 is small for square root near 9, where curvature is mild but not so small for x to the 10th near 1, where curvature is steep, and we saw the error reflect that. It fails in 3 ways. First, if f prime of a doesn't exist, corner like absolute value at 0, cusp like x to the 2/3 at 0, vertical tangent. There's no tangent line, no linearization, end of story. Second, if you push x too far from a, you're extrapolating outside the regime where the line tracks the curve and the error explodes. Third, if f double prime is huge, meaning the curve bends sharply at a the second derivative correction kicks in immediately even for tiny steps. The fix in all cases except the first is to add more terms. Take the linearization, then add a quadratic correction, then a cubic, then a quartic, and so on, and you get the Taylor series, which is the proper generalization of linear approximation to all orders. We'll come back to that. For today, the linear story is enough. Where we landed, the big idea, up close, every smooth curve looks like a line, and we can replace the curve with that line for local computations. The line is the tangent, the formula is the linearization, L of x equals f of a plus f prime of a times x minus a, and differentiability is precisely the statement that this best linear approximation exists. We approximated the square root of 9.04 to 5 decimal places in one line. We approximated 1.02 to the 10th to within 2% and saw the second order correction account for the gap. We met differential notation, dy equals f prime of x times dx, with a history from Newton's moments to Leibniz's infinitesimals, to Cauchy's limits to Cartan's forms and Robinson's non-standard analysis, and concluded that you can take it literally with confidence. We propagated measurement error. A sphere's radius known to 1% gave a volume known to 3%, with the factor of 3 coming directly from the exponent in the volume formula. And we listed the engineering payoff, every linear circuit model, every small angle pendulum, every linearization around an operating point in control theory. Every Newton method iteration is this episode in disguise. Next time, local extrema and the mean value theorem. We use the derivative to find peaks and valleys, and we meet the theorem that ties average rate to instantaneous rate, the workhorse result that justifies a surprising fraction of everything that follows. See you in episode 11. Linear approximation is calculus, admitting it cannot solve every problem exactly, and then succeeding anyway by being correct to first order. The channel works the same way. One share, one comment, one subscribe, each is small, each is linear, and together they add up to growth that's anything but. Thanks for being part of the slope. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.